Okay, so today's topic is important applications of Gauss theorem. Uh, now, under this, we are going to see electric field intensity due to an infinitely long straight uniformly charged wire. Lengthy topic, right? Electric field intensity due to an infinitely long straight uniformly charged wire. Okay, now for that, so we are going to find out the field intensity due to this. So consider an infinitely long infinitely, it is going this side and here also, infinitely long thin wire, okay, and here the charge here on which let it be positive charge, uniformly it is distributed. Okay, let this what is that, linear charge density, because the uniformly distributed now, and let the linear charge density of this wire, let it be lambda. Okay, now we are going to find out the electric field due to this long wire, charged wire, at a point that is P. At a point P. Okay. So we have to find out both magnitude and direction of the electric field intensity at the P. Right. Okay. So now what you have to do, the perpendicular distance of that point, okay, from the wire is, let that be R. Distance is R. Okay. So before going to the magnitude, we are going to find out both magnitude and direction. First, we will fix the direction. Okay. So for that, what I am going to do is, let me take two small elements, linear elements. Okay. Symmetrically on both sides of the this perpendicular distance, and the perpendicular distance, it starts from O. Okay, OP, that is equal to R. So I'm taking two elements, let that be the P1 and P2, and these two elements I have taken on symmetrically on both the sides of the sides of O. Okay, so from O only P is at a perpendicular distance, that is R. Now what are we going to do? We are going to fix the direction. Okay, so for that, what you have to do, see, due to P1, P1 has a small element, that will positive charge will be embedded there. Okay, therefore what is, I want electric field at P due to P1. The element P1. Therefore, if I keep a unit positive charge there, therefore, what will be the direction of the electric field due to P1 here? Okay, and it will be in this direction, right? Okay, therefore, let it be E1. Due to P1, the electric field is E1. Like that, I am going to take a P2. Due to P2, what will be the, now I am finding only the direction. What will be the direction of electric field at P due to the element P2? Therefore, that will be, see, it will be in this direction. Both are symmetrically, what is it, on both the sides of O. Okay. Therefore, now if I take P1 and P2 like this, therefore, how to find out then net electric field due to P1 and P2? Once again, what you have to do, you have to resolve E1 into two components, one in this direction and the other one in this direction. Correct? Like that, you E2 also, you resolve E2 into two components, one in this direction and the other one will be in this direction. Okay. Therefore, see, these two components I have taken symmetrically on both the side of O, and the element length is also same. That is, length of the element is also same. Therefore, number of charges there, because since it is uniformly distributed, number of charge in the element B1, that P1 is equal to P2. Therefore, definitely, what is the electric field? E1 and E2 magnitude wise both have to be the same. But if I am resolving it, this, see, towards the right, this one and this are equivalent, opposite, therefore they cancel each other. So what will be the net electric field? Net electric field will be in this direction. Are you following? Therefore, what is that? This is the direction of the electric field, okay, at P, due to what? Due to the element, that is P1 and P2. Okay, right. Therefore, now what, like that, if you take two elements like this, symmetrically opposite in both the directions of what is that O, because it's infinitely long wire. Therefore, if I take two like that, the net electric field always it will be, what is that? Outward, radially, you can say it is outward, along outward, you can say normal. Okay, therefore, whether you take here and here, that time also you will be getting the electric field direction will be only, what is that? Outward, and it is normal to the line. Okay, therefore, what will be therefore? Definitely, if we take paper like that, all the right and left side components will cancel. Only the perpendicular component, which is the component which is perpendicular to the line of charge, will be a non-zero one. Everything will add up. So, net electric field will be, what is that? Along, in the direction, in which direction? Radially outward. Okay, right. Therefore, it is now. So now what is that? Electric field direct intensity is, direction is fixed. Okay. Now what I want? Okay, I want to find out the magnitude. So for what should I do for that? Let me take, see, okay, for magnitude, okay, so now I have fixed the direction. Now what I want is the magnitude. Okay, so let me have okay, here I'll draw. See, this is once again, because this is the charge having the linear charge density, it is a element, that is a line of charge, okay, having a linear charge, that is a charge density. Here is, what is that? It is uniformly distributed now, therefore it is okay. And so what I want to find out the same here. The point of my interest here is what is it? P is here, and the distance is, what is the distance from the what is that line of charge will be R, correct? This is R. This is R, perpendicular distance. Okay, now, so I have to find out the magnitude. So how to find out the magnitude? For that you have to go for what you have to apply Gauss theorem. So if you are applying the Gauss theorem, then what you have to do here is you need a Gaussian surface. You need a Gaussian surface. Why? What is Gauss theorem? Once again, it is the surface integral of the electric field over a closed surface enclosing a volume V in vacuum, or the electric flux, okay, over a closed surface in vacuum, okay, that is equal to 1 by epsilon naught times the total charge enclosed within the surface. So I need, if I have to apply Gauss theorem, I need a Gaussian surface. Okay, so what I have to do? So which is the proper Gaussian surface? See, according to my what is that charge distribution here, linear charge distribution line, therefore which can be a proper Gaussian surface. So if you think that has to be what is that here, it is extending in, okay, it is here, it is going both the side, right? Therefore, what should be the proper Gaussian surface? It should be right circular cylinder, okay, such that the point of interest lies on the curved surface of the cylinder. Okay, and the cylinder, what is the radius of the cylinder? Radius of the cylinder is nothing but, because my point is lying on the surface, the curved surface of the cylinder. Now, therefore, radius of the cylinder has to be r. That is the distance, okay, of the point of our interest where we have to find the electric field, right? Therefore, it is a cylinder. Therefore, let me have cylinder of, I'll take a length that is L. The cylinder of length L. This is my Gaussian surface. Okay, right, done. Now what I have to do, I have to apply Gauss theorem. For applying Gauss theorem, I cannot apply the whole cylinder together first, all together. So what I am taking a very small, what is that, area element, okay, a small surface area, that is here I am taking like this. Let me have some other color. Okay, this is the area, okay, around that point of interest. Okay, therefore, what will be the direction of the electric field here? Now, just now we have found out what is electric field. Electric field direction will be in this direction, that is E, right? So, this is the electric field direction, right? Now, what is the direction? Because I am going to apply, what is the Gauss theorem? Gauss theorem, that is phi, what is the integral E dot ds. I want integral E dot ds. Therefore, here this surface is ds. Therefore, what will be the direction of ds? Direction of ds will be along the outward normal. Now, already we have seen. Therefore, ds direction will be in this way. Therefore, here E and the area vector. Area vector, this is area vector na, direction of area vector. So, E and area vector both are in the same direction. In the same direction. Okay, therefore, if you take everywhere, so many area vectors, if you take area, ds like that, everywhere, what is that, area vector will be in this direction only. Therefore, it is always in the same direction as that of E. Fine. Are you following? Therefore, what is, let me, that is, okay, what is the contribution now? What is the contribution of electric flux, okay, over the curve, by the curved surface? Contribution. Now I am dividing it to two. One is a curved surface, dono side mein. This also, okay. This side also. This is also distance. Therefore, here what will be the direction of electric field? Here the electric field direction will be, what is that? In this direction, right? Electric field direction will be like this. Just, are you following? And if you take ds here, that normal will be in this direction. Wherever you take, okay. So now let us consider only the top portion. Wherever, if you take the, my point of interest is here somewhere also, the same thing, because electric field will be in this direction, and area vector, if you take area vector, that will also be in the same direction. So therefore, now what can what can be written here? Contribution to electric flux, okay, electric flux over by, you can say, contribution differs flux by the curved surface, okay. Therefore, that is nothing but, what is that? That is equal to, okay, integral E dot ds, correct? And that is equal to integral of, okay, E dot ds, E dot n ds, correct? And that is nothing but, okay, E Okay, E and N both are in the same direction. Therefore, you can write E, okay, ds. E and N are in the same direction means cos 0. Okay, and cos 0 is equal to 1. Therefore, I can write it is E, okay, ds. Same thing. Okay, right. Therefore, that is nothing but E into ds. ds here, what is the area of the curved surface of the cylinder? Now, I want it is only, I have taken only this surface, curved surface. Okay, there are end surfaces also there that I have not considered so far. Only curved surface. Therefore, what should be the area of the curved surface is equal to 2 pi rl? 2 pi rl. Are you following? Therefore, this is 1, right? Next one, but your cylinder has two end faces also, right? So the end faces, I am okay, this face. Okay, so these end surface is there now. This end, so the curved surface contribution we have found out. Now we have to see end surface. For end surface, what is the area vector? Just you see what is the direction of area vector. Area vector will be always outward normal, means here it will be n. If you take this side to the left side of the cylinder, what is n? This will be n. Okay, therefore that is ds direction will be, what is that? At let me give one name to AB. Okay, at A it is towards left ds. Okay, outward normal no area vector. So for this area that what is that here, it is circular na. For this end surface, okay, area vector will be in this direction, that is left, and at B it will be towards right. Okay, right. The area, let whatever is the area, that I am taking small ds only here about ds. And what will be the electric field? Electric field will be in this direction, correct? Electric field is in this direction. Therefore, what is the direction between the electric field and the area vector here is normal? Now is 90 degrees, because area vector and the electric field are actually perpendicular. Are you following? Therefore, what is the contribution? E dot ds, E and ds, area vector direction, both are perpendicular, means what is the electric flux here? The electric flux will be 0. Therefore, contribution to electric field by the end surfaces. Okay, that is integral E, okay, ds cos 90 angle. Therefore, that is equal to 0. That is, therefore, contribution to electric flux is only by the curved surface. There is no contribution by the end surface, right? Therefore, what is the net? What is the total? Total electric flux okay, over the whole cylinder. Okay, that is given by phi. Okay, and that is nothing but, what is that contribution only by the curved surface? Already we have seen that is nothing at E into 2 pi rl. We have already seen na? E into 2 pi rl. Okay, therefore, now what is the, and according to Gauss theorem, okay, by Gauss theorem, phi E that is equal to, what is the total charge enclosed divided by epsilon naught. Okay, now we want what is Q here. What is Q here? Q is nothing but what is the length of the cylinder, only for that length. Gaussian surface ka length is L. What is your, this is equation number, I think let it be 2 or whatever, it's 1. Okay, okay, therefore what is that, phi divided Q divided by epsilon naught. What is Q here? Q is nothing but charge per unit length, linear charge density is L. But what is the length of the cylinder? Lambda L. Length of cylinder is L. Therefore, total charge Q, that is equal to lambda into L, correct? And divided by epsilon naught. Divided by epsilon naught. Therefore, this is 2. Okay. Therefore, you can say E into 2 pi RL, that is equal to lambda L by epsilon naught. On applying Gauss theorem, flux is nothing but 1 by epsilon naught times the total charge enclosed within the surface. Total charge enclosed within the surface is given by, once again, what is that? It is lambda into L, where lambda is the linear charge density, L is the length of the surface. Okay, that is cylinder. The Gaussian surface what we have taken is a cylinder. Okay, therefore, now you tell me what will be our, this one, therefore L will get cancelled. Okay, therefore what is your E? E, that is equal to lambda by 2 pi r epsilon naught. Okay, therefore this is the final expression. Therefore you can say that E is inversely proportional to r. Okay, so it depends only on the distance, perpendicular distance from the line of charge. Okay, it is independent, where, because the wire is infinitely long. Okay, it depends only on the perpendicular distance from, okay, from the line of charge. Okay, therefore if what is the direction? If lambda is larger than 0, that is positive, charge is positive, then direction of E is radially outward, correct? But if lambda is less than 0, direction of E is, see here lambda, let me have one, see here lambda is like that. Therefore E direction will be, what is E? E will be in this direction, correct? Radially inward. Therefore is radially okay, outwards, it is inwards. Okay, therefore this is, if your charge density is what is the charge density is less than 0, which means a negative. Okay, therefore lambda, that is equal to Q by L. Therefore charge Q is a negative, means then lambda will be negative, that time it is radially inwards. But if it is positive, charge is positive, okay, then it is radially outward. Is it clear? That is it. Okay, right.